Hi everyone, welcome back. So today we're going to be talking about the disk and washer method. And as we'll see, one of these is just a special case of the other. But again, what we're doing here is we're going to be finding a volume. But this time, instead of slicing it up into cross sections, what we're going to do is we're going to take a region in the XY plane, like I've drawn here. We're actually going to take it and revolve it around an axis. So generally this is either the X or the Y axis, although it is possible to have different ones. But generally what we're going to do is we're going to take this region and we're going to rotate it around an axis. And in doing so, we take this point here, and we notice that when we rotate it around, we draw out this giant circle like this that goes around that point. We can do the same for one on a vertical line down here and draw a slightly smaller circle that pops out around the axis like this. And we notice that if we were to divide this region up into a bunch of bars like this and trace them out as we've just done, we'd essentially be summing up a whole bunch of washers, right? So we have this bigger circle, we're subtracting out this inner circle here to get a little tiny piece of the volume. And the last thing we have to do is we have to extend it out a little bit and make it this fully three-dimensional washer with some width element dx that we give it. Okay, and this functions just like the cross-sectional method. So what we're going to do is we're going to find an area of a single washer. We're going to make this as general as possible. So we're going to keep it in terms of x or in terms of whatever variable we need. And then we're going to multiply it by dx. And then again, if we integrate over our entire bound from a to b, we should get the volume of the entire solid when we rotate that region around one of the axes. Okay, so again, the name of the game here is finding the area of the washer. That's going to be the most difficult part. So let's go ahead and just jump right into some examples here. We have the region in the XY plane given by y is equal to x, and we're going to section it off here when y is equal to 1, and we're going to be dealing essentially with this part here. I should note that when we find the area of a washer, what we're doing is we're finding the area of two circles, right? So the area of the outer circle is equal to pi, I'll call it big R squared, and the area of the inner circle is equal to pi little r squared. So the area of the washer is equal to the difference of those two, right? R squared minus little r squared. And so what we need to do then is we need to figure out the big R and the little r and essentially find the area of the washer that way. Okay, so we're going to be revolving this region around the x-axis. It's going to trace out some sort of inverted cone-looking thing, so they'll look, something like this. But it doesn't really matter. What we need to find is the inner radius and the outer radius. So we pick any arbitrary point. Let's do it this one. We find the maximum distance that that region reaches away from my axis of revolution. Okay, so I'm going as far as I need to go to get the outer edge. That outer edge here is given by just the function y is equal to 1. Let me do this better. Y is equal to 1. My inner radius is just, as far as I need to go before I start to hit my region, and I go all the way up to this line here, which quite simply is given just by the line y is equal to x. And essentially we have everything we need. So I can say that the volume then is going to be the integral of pi, my big R squared is 1 squared minus my little r squared is x squared dx. All that's left is to find the bounds. We're integrating with respect to x, right? So I need to do this at every single x point. So I keep going until I reach this point here, which happens to be when x is equal to 1. So I'm going from 0 to 1. If I do this integral out, I should get 2/3 pi. Okay, so this is almost as simple as it gets, right? You're identifying an outer radius and an inner radius. The formula is not going to be that terrible, and you're going to get an answer in terms of pi generally. All right, so let's do another example. We have the region bounded between two curves this time instead of just a line and a curve. So we have x and y here, and then I have one of my lines here is y is equal to 2x. The other one is not very well drawn, but y is equal to x squared. And what I'm doing is I'm revolving this region caught in between the two of those around the y-axis. So again, what we need to do is we need to find our outer radius and our inner radius. So our outer radius is going at any arbitrary y value all the way out to that function on the outside, which is y is equal to x squared. So we can write that down. Oh, wrong y. Y is equal to x squared. And then it's going all the way to the inner part here, just before it starts to head into the region, is at the function y is equal to 2x. So what we can do is we can, similarly set up our integral here. We have the integral from pi of x squared squared. So I get x to the fourth minus 4x squared. But I run into a problem here. Okay, and this is what you need to be careful of. I'm integrating with respect to y. So what I'm doing is I'm doing this little washer here around this axis. So if I want to draw the next one, I move up a little bit and draw the next one. And I move up again and draw the next one. So what I need to be very careful of is I need my equations to be in terms of y. Okay, so it's not actually y is equal to x squared. It should actually be x is equal to the positive square root of y, because we're in the first quadrant here. And then over here, x is equal to 1/2 y. So I really hope that was clear. This is not correct. And if you're listening to this without sound or you stopped there, that might be a problem, but whatever. Our integral then should be integral of pi. Big R squared happens to be square root of y squared. And then little r squared happens to be 1/4 y squared. You take the difference of that, and we're working with dy, right? So I need my bound to be in terms of y. So I start all the way out here at the origin, which is when y is equal to 0. And I go all the way up to this intersection point here. This point intersects when x is equal to 2, but we're not going in x, right? We're going in y, and y is equal to 4. So that was a little tricky. If you do this integral out the way I did, which might not be correct, you get 8 pi over 3. Okay, so again, it's very important you keep track of which variable you're integrating with respect to and make sure your functions inside your integral match that. In other words, you don't want functions of x here and then the dy. That's a problem. All right, our last example here is going to be simpler than that one. We're going to go simply with the function y is equal to e to the x. We're going from x is equal to 0 to x is equal to 1 right here. So it's just this part. And we're going to revolve this around the x-axis. So again, what I'm going to do, pick an arbitrary x, go all the way out to the outer bound here to find my big R. My big R happens when y is equal to e to the x. And then my little r, and this is where it gets interesting, kind of, is right when we begin. Right, so my region that I'm integrating is right up flush against the axis of revolution. So there's not going to be any space here. There's not going to be a little circle I subtract out. So my little r here is when y is equal to 0. And this is what's known as the disk method, right? So up here, I have washers. I'm subtracting off a little piece. It looks like a washer, when you build IKEA furniture. Here I have just a disk. There's no hole in the middle, so it looks like a Frisbee. I know Frisbees sometimes have holes in the middle, but a typical Frisbee then. So then if you want to find the total volume, you integrate from x is equal to 0 to x is equal to 1, simply just e to the 2x dx. If you integrate that, you get pi halves e squared minus 1. So remember that e to the 0 is not 0, it's actually 1. And this is what you end up with. So this right here is the disk method. And the special case scenario I referred to earlier is simply when your radius is 0, right when your region is flush against your axis of revolution. The rest are washer methods. So I hope this was pretty helpful in going on. Next week we'll talk about the shell method and how you can use that to make your life a lot easier.